So, welcome back. In the last session, we looked at the unification algorithm, which is used for making inferences in implicit quantifier form or implicit quantifier notation. We saw it in the context of forward chaining, but as we will see as we go along, in any other form also we will use implicit quantifier form. So, we will not any henceforth we will not use the quantifier symbols. This thing. So, what we had said was that for universally quantified variables, you prefix a question mark in front of the variable name to mark that it is universally quantified, which means implicitly there is a universal quantifier sitting at the very left of the formula, but it says that it is not, we have not written it down. What about existentially quantified variables? So, we did mention some case here, but let us talk about that. When the existential quantifier is not in the scope of any universal quantifier, then the variable it quantifies is replaced by a Skolem constant. Remember, we said that Skolem was the logician or mathematician who came up with this idea first. So, look at this examples. This says some students are bright or some student is bright essentially, which we are writing as exists Z, student Z and bright Z essentially. So, I have written them in both the forms that we have looked at. The expressions in red are in mathematical notation, the expressions in black are in list notation, but they are talking about the same thing essentially. The second one says there exists a girl such that for all boys the boy likes the girl essentially, okay, some very popular girl. You could have said it like this. So, these will be Skolemized because the existential quantifier is not in the scope of any universal quantifier, we will just replace them by Skolem constants. So, in the first example, we will simply say instead of Z, we will simply write SK1 there essentially in both the positions. In the second example, we will replace that y, that girl y for all exists y, we will replace y with SK2. Notice we have chosen a second constant name SK1 and SK2. Whereas, x which was universally quantified, it remains universally quantified in our formula and we use that notation that we have, implicit quantifier notation of putting a question mark below that. Now, what when it is within the scope of a universal quantifier? So, when the existential quantifier is in the scope of one or more universal quantifiers, then the existentially quantified variable becomes a Skolem function of the corresponding universally quantified variables essentially. So, this example should make that clear. So, here is the first example. It says, so let us read that logical thing which is in the red, which is kind of little bit easier to read, even though the first one is easier to process if you are writing programs. So, the sentence is saying that for all x, for all y, there exists a z such that x is less than z and y is less than z. So, we are obviously talking about numbers or something here. So, we are saying that you give me any two x and y and I will give you a number which is greater than both of them essentially. So, here the variable z is in the scope of the two variables y. You can see that for all x, for all y in the top line, that is the whole sentence is the scope for that, because the notation in list form was you write the variable name and then in brackets you write whatever is inside the scope of that. Also, you would notice here that we have kind of clubbed x and y together. Instead of saying like this for all x, for all y, we have said for all x y, both are allowed. we could have also written for all x, y. Okay, so there is another example here. This says for all x, if x is a boy, then there exists a y where y is a girl and x likes y. So, you can see that this also is a kind of little bit of illustration of how to write first order logic sentences. The first sentence is that there is a girl. Okay, we saw that in the previous example. There is a girl who here we saw this here, that there is a girl who every boy likes essentially. And then now we are saying something different. Now we are saying every boy likes some girl. Now in English language, this could be confusing. You could simply say every boy likes some girl, or everyone likes some girl, or something like that. What is the real meaning of that essentially? So, when we write this in logic, you can see that the meaning is clear. In one case, there is a girl who everyone likes. That could have been also said as everyone likes some girl. In the second case, for every boy, or for in this case there are boys, for every boy there is a girl who the boy likes. We could have said that also in English as every boy likes a girl essentially. So, is that a girl specific to the boy, or is it for everyone? Is not clear in English language. English language is that way ambiguous, but logic makes it very clear essentially here. So, anyway, in this example on this page, the two sentences both have existentially quantified variable in the scope of universally quantified variable. In this case, y is in the scope of x, and in this case z is in the scope of both x and y. So, the Skolem functions must be constructed appropriately, and they will be that in the first case when z is in the scope of both x and y, it becomes a Skolem function. So, we use similar names for functions also, because the context makes it clear. So, this function is called SK57, and it is a function of both x and y essentially. In some sense, we are saying the value of z depends upon the value of x and y. In that sense, it is a function. It is not a function in the sense that 2 plus 4 will always be 6. So, here here the function is some kind of a dependency, that z, the value of z that will make the sentence true depends upon the value of x and y. So, that is why it is a function of both essentially, and in the second example we have SK16, which is a function of x essentially, because that girl is specific to that boy essentially. Now, remember the rules of substitution we had talked about earlier. So, just a very quick recap. We had the De Morgan's laws, which said that you can push the not inside, we can push it across the quantifier, but it will change the nature of the quantifier. So, when you move the not inside, the universal quantifier becomes existential, and the existential quantifier becomes universal essentially. And I had suggested to you that if you think of the universal quantifier as a very long and, it is true for the first element in the domain, second element, third element, you could think of it as a proposition formula. Then the De Morgan's law, you can see that it is doing the same thing here as well. And we had said that you can always exchange the order in which you write same quantifiers essentially. And we have seen with this boy girl example that changing the order changes the meaning if the quantifiers are different. So, if I say for all x there exists a y such that p x y, this is not equal to there exists a y such that for all x p x y. In the second case, the y is fixed first, and then we are saying that for every x that is true. In the first case, we are saying for every x there is some y essentially. So, obviously, the meaning is not the same, and therefore, you cannot swap different kinds of quantifiers in an expression. But if they are the same, like in the examples given here, then you can swap them and it does not change anything. Sometimes it is not so clear as to whether a variable is universally quantified or whether it is existentially quantified. So, let us look at a few examples to help us clear that part. So, here I have said that whether a variable is universally quantified or existentially quantified has to be decided very carefully. One must keep in mind that the negation sign influences the nature of the quantifier. That is why we did the recap of the De Morgan's laws essentially, that if you push a negation inside, it will change the quantifier. So, think of this sentence, we want to say no one is immortal or an immortal man does not exist, they are the same thing, right, which is another way of saying all men are mortal. So, when you say all men are mortal, the negation of that is no man is, the negation of that is there exists some man who is not mortal. So, when we want to say that an immortal man does not exist, so immortal we will see, we will treat it as not mortal essentially. That is how it has been written here. So, immortal is same as not mortal essentially. We want to say that an immortal man does not exist. So, we are saying it is not the case that there exists an x such that x is man and x is not mortal. What is the nature of x here? Syntactically, there seems to be an existential quantifier there we said there exists an x. So, on the surface it is bound by an existential quantifier, that is what I have said here. So, one might mistakenly Skolemize it as saying that replace it with a Skolem constant, but that only talks about a specific albeit unspecified individual or individuals. So, this sentence with the Skolem constant says that it is not true. So, essentially this sentence will have the existential quantifier outside essentially. There exists x such that both these things are not true essentially. The correct way to Skolemize the formula is to first push the negation sign inside. So, once you push this negation sign inside, once you push it across the quantifier, it will become a universal quantifier, and then you can see that it is a universally quantified variable. You are saying that for every x, it is true, it is not true that x is a man and x is not mortal. So, the simple lesson is you must push the negation inside before you decide whether the variable is universal or existential. So, look at this sentence, if there exists a number that is even and odd, then the earth is flat. Now, we have written this as follows. So, this is the antecedent, if there exists a number such that x is even and x is odd, and then the consequent is earth is flat, it is not connected with x at all. We could now use some of our rules of substitution here by saying that this implication we will replace it by this thing and by adding a negation of this. Remember that we said P implies Q is equivalent to not P or Q. That is what we have done here. Then we push the negation inside and that is what we get, and we do a little bit of more of this processing, and eventually we get the same sentence that x is a number and x is even and x is odd. This implies that the earth is flat, but the quantifier has become universal. So, what this seems to suggest is the following, is that because in this antecedent there is an existential quantifier. So, the antecedent is P here, but there is a hidden negation in that already essentially. So, if we push, if we do this process that we just saw, you can see that this is really a universally quantified statement. So, when we say if there exists a number, so if you say if there exists a unicorn, then something something something, we are equivalently saying that for all x's that are unicorns, or for all numbers that are both odd and even, they will imply that the earth is flat essentially. Another example will make it finally clear, I hope. So, this says that a detective without a sidekick is successful. You know, if you have watched detective serials, they always have a sidekick essentially. You know, Sherlock Holmes had Watson, and everybody has somebody on the side. This also shows that a quantifier in the antecedent of a implication statement has to be treated carefully. So, what is this saying? A detective who has a sidekick. So, for all x, if x is a detective and there exists a y such that y is a sidekick of x, then x is successful. So, what we are saying now, be careful, this existential quantifier is in the antecedent of the implication sign, and therefore, there is a not hidden there already. So, be careful how you think of y. Is it universal or is it existential? On the surface it looks existential, but if you now simplify this formula, again we have done the same thing. We have replaced this thing with this thing and added a negation before that. Then we have simplified this, we have pushed the negation inside, then pulled the universal quantifier outside. That can always be done, and we will look at a procedure later when we will do this. And then we have basically a universally quantified variable. So, what this is saying is that for all x, for all y, if x is a detective and y is a sidekick of y is a sidekick of x, then x is successful, which is what we said in the first place, that for all x, if x is a detective and there exists a y such that y is a sidekick of x, and then x is this thing. So, the lesson to learn is that whenever there is a quantifier in the antecedent, it usually means the other quantifier, if you manage to pull it out essentially. So, very quickly, Supposing we have Skolem constants in our knowledge base, because we have existential statements, can we use them in proofs? So, here is an example. The first sentence is there exists an x such that x is even. The second sentence is for all x, if x is even, then x is not odd, and you want to infer that there exists a number which is not odd. We Skolemize them as follows. The first one says some even number. So, instead of using an SK name, I have just used a name like this. So, there is some Skolem constant which is an even number. So, the Skolem constant is a constant, we do not know what it points to. All it says is that there is something in the domain which satisfies this property. That is because in the existential statement we do not know which x we are talking about. The second one is of course universal. It says for every x, if x is even, then x is not odd, and we can simply just go ahead and use our standard substitution unifier and infer that there is some even number which is not odd. So, that works. A constant, a Skolem constant can also be thought of as a function of arity 0, but that is besides the point. Skolem functions are also simply treated as functions essentially. So, here is an example. The first sentence is for all x there exists a y such that x loves y, everyone loves someone. The second sentence says for all x for all y, if x loves y, then x cares for y. If someone loves somebody, then they care for them. That from this we want to infer that everybody cares for someone. Now, obviously, it follows logically, it is entailed because you are saying everybody loves someone, and then you are saying that whoever you love, you take care of them. So, obviously, everybody takes care of someone, but Skolemization should not get into a way of making this inference, and that is what we want to show here. The first sentence has a Skolem function, because y is in the scope of this universal quantifier there. So, it gets transformed into SK7, which is the Skolem function of x. The second one is entirely universal, and then we use this substitution, we can come up with the desired conclusion, which is that everyone cares for someone essentially, and that someone is not arbitrary, it is somebody they love actually. Okay. So, in some sense we are done with forward chaining, we are done with Skolemization, implicit quantifier form. When I come back, I want to talk a little bit about the application of forward chaining in the real world, in the industry world. We will start with a small introduction here, and later in the course we will look at some details of how that is really done in the industry.